Hello, my name is Hans Hanley, and I'll be presenting the work TATA, Stance Detection via Topic-Agnostic and Topic-Aware Embeddings. On social media, forums, and newspapers, professional commentators and laypeople often give their opinions on a large range of events, people, and social phenomena. Understanding how these individuals approach these issues is important to gauging public opinion and perception, understanding changing attitudes, and making public policy decisions. To try to properly model online attitudes on a wide range of different topics, stance detection is often used. Stance is defined as the expression of a speaker's attitude towards a particular topic. Normally for stance detection, a model takes as input a passage and a target/topic, and outputs the attitude of that passage to that topic. For instance, a stance detection model that took as input the passage, "Lincoln was a good president," and the topic/target of Lincoln would output that the passage's stance towards Lincoln was pro-Lincoln. Stance detection is often highly dependent on the target/topic, and features that are useful for predicting the stance for one topic can sometimes not be useful for other topics. For instance, features that would be useful for predicting the stance of a passage towards abortion would often not be useful for determining another passage's stance on charter schools. As a result, stance detection models are often highly dependent on the domain on which they are trained, often failing to generalize to domains and topics outside of the training data. To test a model's generalizability, stance detection models are often benchmarked in zero-shot and few-shot settings. In the zero-shot setting, models predict the stance towards topics that were not in their original training data. In the few-shot setting, models predict the stance towards topics for which they had few training examples. One of the most widely used datasets to train and test models for the zero-shot and few-shot settings is the Varied Stance Topic Dataset, or VAST dataset, released by Alloway et al. In 2020. To better stance detection generalizability, prior work has looked at clustering the VAST dataset to create generalized topic representations and inserting targeted outside information, among other techniques. In this work, we extend this past research, proposing our TATA model for stance detection. This model takes advantage of contrastive learning techniques to design pre-trained topic-agnostic embeddings that learn general stance features and pre-trained topic-aware embeddings that learn to differentiate between different topics, achieving state-of-the-art results on the VAST dataset. Within our work, to train topic-agnostic embeddings that learn general stance features, we apply contrastive learning on an extended VAST dataset to create distinctive embeddings for each stance class, those being pro, against, and neutral. To extend the VAST dataset, for each passage topic pair within the original dataset, we utilize pre-trained paraphrasers to create differently worded versions of the original passages and topics. We specifically used the Dipper paraphraser that was fine-tuned on larger texts to paraphrase the passages within VAST, and the Parrot paraphraser that was fine-tuned on shorter texts to paraphrase the topics. This allows us to create additional passages and topic combinations, extending the original VAST dataset from 13,477 examples to a total of 743,644 examples. With the input as the passage conditioned on the topic, we use the hidden representations of the CLS token outputted as the embedding, and then proceed to apply a contrastive learning step. This is such that within each batch within our dataset, we consider passage topic embeddings that have the same stance as positive pairs and those that have different stances as negative pairs. As seen in this figure, plotting the TSNE of the embeddings of the VAST validation dataset, as we continue to train using this objective, the embeddings outputted, while not perfect, are separated into the against, pro, and neutral classes. Having pre-trained our tag encoder, we next trained a topic-aware embedding layer to differentiate between different types of topics. To do so, we required a dataset of passage-topic quadruplets, where the two topics were similar. Within each batch, we could then apply contrastive learning, where we could consider the sets of passage-topic pairs that were about a similar topic as positive pairs, and all other pairs as negative, allowing us to learn an informative embedding that can differentiate between similar and dissimilar topics. To create such a dataset, we utilize a set of news articles. Specifically, taking a dataset of news articles, we select 100,000 different articles and extract the first paragraphs as passages. To then identify the potential topic of each of these passages, using the Spacy library, we extract out all the noun phrases contained in the passage. We then utilize a pre-trained T5LAM model to pick the topic amongst the different noun phrases. Having extracted different passages, as well as their potential topics, we subsequently identify additional passages within the original news dataset that are topically similar to the original passages using the pre-trained MPNet model, fine-tuned for semantic similarity search. Lastly, we apply the Parrot paraphraser on the extracted topics, finally outputting topically similar passages with shared paraphrased topics. Having constructed our dataset, we train our topic-aware or TA encoder using a triplet loss and using the DeBerta contextual model to embed each passage topic pair. Within each batch, we consider the sets of passage topic pairs that were about the same paraphrased topic as positive pairs, and all other pairs as negative. We utilize a held-out set of 10,000 passage-topic quadruplets as validation. Once our tag and TAT encoders are trained, we combine them into one model, TATA, following the embeddings of the tag and TAT models with attention layers with the output of a DiBerta model, and finally outputting the stance class using a 2-layer feed-forward network. Training our TATA model using the original VAST dataset, we achieve state-of-the-art results on the VAST test dataset in both zero-shot and few-shot settings. Performing an ablation study, we further note that the models trained using just our TA and tag embeddings also outperform the previous state-of-the-art. On several challenging linguistic phenomena for stance detection, such as sarcasm and passages containing multiple topics, we further note that our TATA model also improves upon prior work. Finally, testing our models in a zero-shot setting on the 2016 SemiVol Task 6 dataset, we again find that our models surpass prior work. In conclusion, in this work, we curate and release 2 datasets that take advantage of paraphrasing and contrastive learning to create tag and TAT encoders. Combining the pre-trained tag and TAT encoders in our full TATA model, we achieve state-of-the-art performance on the VAST benchmark dataset. Thank you, and you can find me at the following links.